Okay. Today we are going to take the derivatives of the inverse trig functions. Holy smokes, this is nasty. And to be honest, it's not that much fun.
Thank you for your honesty.
Well, it is. The reason I don't like it is because it's just the best way to do it is memorization, and I'm not a big fan of memorization. Okay, so you should be able to, as it says, get a clicker that works. We're going to talk about the 6 trig functions. We've done that already, but just a quick review. And we're going to do some pre-calc review, which will help with that. Then we're going to take the derivative of those inverse trig functions. That'll be fun. Not. And then when we're done with this lesson, we're done with all derivative formulas. So we'll have completed every possibility for derivatives. Therefore, I have a summary chart for you that breaks down every single possible derivative thing we've done this year. And then, of course, last but not least, you should name the presidents in order of descending height.
Can you do it?
No, I know the first and the last. First is Abe Lincoln. Shortest? Madison. You know how tall he was?
6'5", 4.
How do you know that?
I'll look it up.
Okay, he's right. You don't have to look it up.
I don't think he's right.
We looked it up. Well, it is. We looked it up fourth period. Well, go ahead if you want to work the Google.
Do you want to wager on it?
Yeah, I had like $20.
Negative $4.
Negative $4. Wow,
4.
that was mathematically great. So now you owe him $4 there
Yeah.
because he bet negative $4. That was kind of an inverse function bet.
Yeah. It was.
Wow,
Yeah.
that's nerdalicious. Okay. All of this is supposed to be pre-calc stuff, which you did last year. Oh, God. Here we go. Hey, why don't the trig functions have inverse functions? Why, for instance, isn't there normally a sine inverse function? Even though there is, but why wouldn't there be based on what we've done already? Doesn't pass the horizontal line test, correct. The sine function goes on forever and makes those little peaks and valleys, and therefore it wouldn't pass the horizontal line test, which means it wouldn't be 1-to-1. So that doesn't work for us though, because we need to be able to do an inverse trig function. So you'll recall from pre-calc, we have domain restrictions for each of the functions, which you remember, of course, looking something like that. There it is in perfect English. I don't know if we've used this yet. Have we looked at arc? Have we used the arc terminology yet?
No.
Yeah, okay. So it's arc is the same thing as inverse. So the inverse sine function, IFF, anybody know what that stands for? If and only if. Blah, blah, blah. Okay, all of that looks peachy keen. However, there are a couple important things to get out of this. Number one, we're no longer using values in the fourth quadrant as 11 pi over 6, 7 pi over 4, that kind of stuff. We're now looking at it as negative angles. So if you start at the 0 value and you go downward, you're going to go down to negative pi over 4, for instance, or down to negative pi over 2, not 3 pi over 2. You need to know all of these on the side. When you did that last year, you will recall that each one of the functions has one answer in the first quadrant, because they all have Q1, and then the quadrant for their negative answer is in a different location. So if we look at sine, for instance, sine relates to y. Y is positive in the first quadrant, so that gives you the first quadrant answer, and y is negative in the fourth quadrant. So sine is restricted to quadrant 1 and quadrant 4. None of these, just to help you out a little bit, none of them are quadrant 3. Quadrant 3 is a no-fly zone. It's either quadrant 2 or quadrant 4, depending on the function. Some of them are fairly ambiguous as to which one you can use. Sine and cosine you can work out logically. Okay, like I said, you need a y value that's positive, that's quadrant 1. You need a y value that's negative, and you can't go into quadrant 3, so therefore it's got to be quadrant 4. Things like tangent and cotangent can be a little confusing, because you could go into either one, quadrant 2 or quadrant 4. To make matters worse, they put tangent in 4 and they put cotangent into 2. I don't know why. There's probably some weird mathematical reason for it, I just don't know what it is. Please don't copy down the whole grid. This is what you need.
But this will go online, right? Yeah.
scary thing is the first 5 words there, as you learned in pre-calc.
Yeah.
Just like what you should have learned in pre-calc is how to find the value of inverse functions that fall on the dreaded unit circle.
I actually don't mind the unit circle.
I do.
You are a rare individual.
It's pretty fun.
I'll prove the point.
I'll-
How many of you don't mind the unit circle?
It's okay.
Okay.
I'm probably
I'm
probably
indifferent.
wrong, I'm sure.
You're indifferent?
Yeah.
You're like Switzerland?
Yeah.
You're neutral?
Mm-hmm.
Okay, I understand. Take it or leave it. Yeah, like Tom Hanks. He's pretty much.
Yeah. Basically.
Yeah, he's not a pro, he's not a con. He's not, he's just, he's there.
It's kind of there.
Right, yeah. Okay. So based on your vast knowledge of the unit circle, if we didn't have the domain restrictions, that first problem, for instance, would have an infinite number of solutions, right? It would have a negative value in quadrant 3, it would have a negative value in quadrant 4, and then you would have all those values from going around the circle over and over and over again. The idea of the inverse functions now is that we restrict it to domain, we have domain restrictions, which means you get one and only one answer. So where is the arc sine equal to 1/2? Sorry, I said that. Yeah, where is the arc sine equal to, no, I said that wrong. Where is the sine equal to 1/2? In other words, what is the arc sine of negative 1/2? What spot on the unit circle, when you look at the y value of it, gives you a negative 1/2 answer? Is it? Negative pi over 6.
Wait, is that negative pi over 6 or can you say 11 pi over 6?
No, 11 pi over, or sorry, 11 pi over 6 isn't in the domain restriction. We now go positive values to pi over 2, negative values down to negative pi over 2. Which gets confusing because you learn it one way and then all of a sudden they turn the tables on you. Say,
I'm confused, what does the arc represent before?
arc sine is the same thing as the inverse sine. So what you're used to doing is something like, what's the sine of pi over 6?
Oh, what, I have to think about it.
Maybe 1/2.
Can I take that?
No.
No.
I'm like thinking right now. 1/2?
1/2, good. Okay, so the sine of pi over 6 is 1/2. So now we're doing an arc sine, which means we want to know what's the arc sine of 1/2 to get back to the pi over 6. So we're going backwards.
Okay.
So we took the sine of a unit circle location and got a coordinate. Now we're taking a coordinate and finding the location.
Oh, okay. That makes
Beautiful.
sense.
Light bulb went on. Where is the cosine equal to 0? That's okay. You trailed off there at the end.
This has nothing to do with the math, though.
I understand.
Arc and not inverse, like,
I don't know.
you decided.
They're interchangeable. It's like
Okay.
it's like y prime versus dy dx. I think it's just different notation. For me, the reason I went with arc is because it's easier to type arc than it is to go in and find it. You know, then I got to do like this weird. Yeah. For me, it's pure laziness for typing these things out. Yeah.
Can you repeat what you said to Mercedes? That made the light bulb go off.
Normally, we take the sine of a location and get a coordinate. Now what we're doing is taking the coordinate and using an inverse function to get back to the location. Okay. So cosine of 0 is pi over 2. Okay. Arctangent of square root of 3. Yes, sir.
Why not 3 pi over 2?
Because 3 pi over 2 isn't in the domain restriction.
So we have to memorize.
Could you do negative pi over 2?
I believe if you go back and look at the grid, I believe it includes pi over 2, but not negative pi. It's a greater, or equal to, less than, and less than thingy jobber. Tangent always confuses people. The way that I do tangent is I think of that as the square root of 3 is the same thing as the square root of 3 over 2 over 1/2. In other words, I want a y value of the square root of 3 over 2. I want an x value of 1/2, and that happens at
Pi over 4. 6.
pi over 3. And we'd get there eventually.
Let me go around in circles.
What is it, 3 over 1?
Square root of 3 over 2 for y, 1/2 for x. Big Y, little x. And then last but not least, that is not on the unit circle. Since it's not on the unit circle, I can't use the unit circle to solve it, so I have to, in this case, use my calculator. So get out your calculators. I want to make sure everybody's got it set correctly and knows how to do it. Take the arc sine of 0.3. That's above the sine button, so second sine of 0.3. Number one, if you use the correct button, and if you're in the correct mode, you should be in the radians. You should get 0.305.
Yeah.
If you didn't, one of those two things is wrong. You're in the wrong mode, or you use the sine button and not the inverse sine button. We having fun yet?
No.
Because of course this is all review. Let's keep chugging along. Now we're going to start combining functions. We're going to combine a trig function with an inverse trig function, and hilarity ensues. First things first, if you take a function and you put it into its inverse, or you take an inverse and put it into its function, you should end up back where you started. It's like putting x squared into the square root of x. They cancel each other out. It would seem like that would be the case with trig functions, right?
Let me guess, it's not.
Not always. So for instance, what is the sine of the arc sine of 1/2? Eric?
1/2.
1/2, beautiful. You know it's not going to be that easy, right?
Where you go.
Right. What is the inverse cosine of the cosine of negative pi over 4? You would think it would be negative pi over 4. And on the quiz or the test when we do this, most of you will tell me the answer is negative pi over 4. But it doesn't work that way because we have quadrant restrictions. Where is negative pi over 4? What quadrant is that in?
2.
4.
4.
Okay, let me do this.
You're close. Sorry. So we get this. What is the cosine value of negative pi over 4? It's 1 over the square root of 2. And then the inverse cosine would put it back in the first quadrant. So it's not always just going to cancel itself out.
Hang on.
I was thinking of the other thing.
Let's do the first one. Where is the sine equal to 1/2? First quadrant at
Number 3.
pi over
4.
6.
pi over 6. What's the sine of pi over 6? 1/2. So we're done. Started in the first quadrant, ended in the first quadrant. This one's different. I'm starting in the fourth quadrant. So the cosine of negative pi over 4, that's in quadrant 4, it's 1 over the square root of 2. What's the inverse cosine of 1 over the square root of 2? When you take the inverse cosine of a positive value, you don't end up in the fourth quadrant. You end up back in the first quadrant because it has to be positive. So that's why that becomes pi over 4. If you're not sure, then just solve it like I did. Don't automatically assume they cancel out. Okay? What about that? They're not even the same function. So forget about canceling out. To make matters worse, 2/3 isn't on the unit circle. Anybody remember how to solve this bad boy?
I don't remember doing that on this.
Yeah.
I remember
I'm
like-
not laughing at you, Abby. I'm feeling your pain. If you didn't hear, she said no, but I remember doing bad on this. So sometimes therapy helps.
I don't remember.
As I show you the technique, it'll come flooding back to you. If it's not on the unit circle and we're combining a function and its inverse function, you draw a triangle.
Oh.
Okay,
Oh,
so
that was like a trick question.
the stuff inside the parentheses, forget about the cosecant out in front, and I know I'm not covering it up, just roll with it. This allows you to draw the triangle. Okay, cotangent is SOHCAHTOA.
Opposite of-
Adjacent over opposite. So here's my angle theta, because I'm dealing, I just call it theta. You call it Bill if you want, I don't care. So I've got some angle that when I take the cotangent of it, I end up with 2/3. Adjacent over opposite gives me that triangle. How long's the hypotenuse?
Square root of
Square root of 13. Good. So now we know the hypotenuse is square root of 13. We know all three sides. Then you forget about the stuff in the parentheses and just take the cosecant of that triangle. And you would get cosecant, 1 over sine. Sine is y over r, or opposite over hypotenuse, so therefore the cosecant would be hypotenuse over opposite, which would give you that.
What?
Can you repeat that?
You did the first one, the middle one first?
Are we okay with this stuff to get to the triangle?
Yeah.
All right, we'll go back to the start. Forget about the cosecant. There is some angle, which I called theta, such that when I take the cotangent of that angle, I'll get 2/3. Which means now I need to remember SOHCAHTOA. Cotangent is adjacent over opposite. So the adjacent side is 2, the opposite side is 3, so that gives me that. Then I do Pythagorean theorem to find the hypotenuse, which is square root of 13. Then the triangle is done. Forget about this stuff inside and just take whatever the trig function is. So just for giggles, I'll tell you. Replace the cosecant with sine. What do you get for an answer? 3 over square root of 13. Opposite over hypotenuse. What's the cosine if I change that to a cosine? What if it's a cotangent? 2/3. Ooh, it cancels. Yeah. That doesn't always happen though. And so once you get the triangle, you can solve all 6 trig functions based on that triangle.
But what happened to the?
Yes, sir. Hold on.
Do we need to rationalize?
No, not in this class, nor for the AP. They don't care. Yeah.
Okay, what happened to the arc and the cotangent?
It goes away. You just use that to get the triangle.
Oh, okay, okay.
So think of this as the cosecant of that triangle sitting over there.
Okay,
Okay?
yes.
We having fun yet?
Yeah.
Especially since this is supposed to be a review. I keep saying that over and over again, but
It's not getting any.
yeah, it's not coming back to you, is it? How about if we don't use numbers and use letters
That's all.
or variables? Same idea. Forget about the cosine. Create a triangle that satisfies that condition. Go ahead, this will be fun. You can call the angle whatever you want. Theta, alpha, mu, beta, epsilon. Oh, no, it's not a Greek letter. Satan is not a Greek letter. Alpha, beta, gamma, epsilon, zeta, theta, alpha, kappa, beta, Satan. No, it's not. As a quick hint here, remember x is x over 1. Oh. If you get your triangle under control and you think you know what you're doing, then take the cosine of that triangle and see what you get for a final answer.
Why are we making triangles?
Because x is not on the unit circle. Or because we're bored and we have nothing else to do. Yeah. What I do in my free time. I understand. You're not quite feeling it.
I'm feeling it, but I'm just like,
How long is the opposite side? Because sine is opposite over hypotenuse. Right? What's the opposite side? X. X. How long's the hypotenuse? 1. Good. Solve for the third side. You showing off. Boy. There you go. Sine is opposite over hypotenuse. X is the same thing as x over 1. Solving for the third side there. Anybody? Good. There you go. And then what's the cosine of that triangle? Well, the cosine of that triangle is adjacent over hypotenuse, which would be, whoops, sorry, that guy. That was fun.
that was exciting.
Uh-huh.
I'm having fun now.
Good. And you can get there eventually. Wait till we get to the calc, you'll have a ton of fun. Notice that's an expression, because there's no equal sign. Well, there's not supposed to be an equal sign.
Oh.
But then you'll also recall solving trigonometric equations. Whoa!
I was good at that exactly.
How do I solve that? You don't is one possibility. Good. Anybody else? What are your options?
Try.
Cry, oh, I forgot crying, yeah, crying's another option.
You take the tangent of both sides.
Take the tangent of both sides. Nice job, Abby, why?
Get rid of the inverse.
Yeah, because taking the tangent of the inverse will cancel out, and we get that. What's the left side become? 2x minus 3. What's the right side become? 1, because the tangent of 5 over 4 is 1, which gets you to this. This is a silly question, but can you all solve that?
I think it was 2.
Have
What
to-
all that now?
Okay, we got your calculators if you need it. 2.
Yes.
I got that.
Got it. Proud of you.
That's like 7th grade math.
Okay, we good?
Yeah.
This was fun, right?
So that,
It was fun.
It's not the worst thing that's ever happened to me.
If it is, you lead a pretty
Yeah,
sheltered
right,
life.
right.
You gotta get out more.
Yeah.
Let's do some calculus! Here we go! Okay, so, you know this already, but I'm not a big fan of memorizing. However, the best way to solve these problems is to memorize. However, I think it's part of my responsibility to show you where these formulas come from. So what we're gonna do first is we're gonna put this bad boy up there.
Whoa.
And I'll show you a trick here. There are 6 of them. The only ones you need to really memorize is the left column. Why?
is the right column the same?
Yeah, right column is the same, just with minus signs in front of it. So if you memorize the derivative of arc sine, then you could do arc cosine by just sticking a minus sign in there. If you remember the derivative of tangent, then you know the derivative of cotangent by sticking a minus sign in front of it. If you want to memorize all 6, you want to waste 6 note cards, go ahead. You only want to use 3, even better. And each one has a subtle enough difference to drive you insane. Because you'll be asking yourself, I don't remember, does that have a square root in it or no? Is that where the absolute value is or does it go on the other one? Does that go on the bottom or the top?
Don't jinx it.
The bottom and top thing is easy. The top is always u prime for all 3 of them. Done. The bottom is where things get a little confusing.
Exciting.
And then notice you've got a 1 minus u squared, you've got a 1 plus u squared, then you've got a u squared minus 1 just to make things even worse.
Where do those equations come?
Has it been?
Where do the equations come?
It's funny, you should ask that.
Don't.
You already did. It's already out there, can't take it back. No take backs. We will talk about the derivation of the sine formula. So I'll show you where the sine formula comes from. The rest are on you. I would guess that most of you will just memorize them. If you have nothing to do tonight and you want to derive the other 5, knock yourself out. Okay, we good?
No.
How about now?
No.
Yeah, I'm ready.
All right, good.
No?
Yeah,
Just
we're
takes
good.
1.
We're good.
No.
Wait, why have we been doing that? You know that other one?
So everything before this was all review. Allegedly.
That's probably like a
I mean, I
really
remember.
bad sign.
I'm really good.
Not very
I'm not that good.
I remember, but the rest of you are screwed.
No, I'm just saying that. I'm just saying I remember doing
You
it.
other peons that don't remember.
I'm good.
Now you're all embarrassed.
Wait, I thought we already took the derivative of that stuff. Oh, this is the inverse.
No, you took the derivative of sine, not arc sine. No way, Jose.
That's the inverse stuff.
Right.
Yeah.
All right, here we go. So, we start with that function. Y is equal to the inverse of the sine. And I want to take the derivative of that. I want dy dx. We'll get there in a second. But first, I want to talk about this. If I start with y and I take the inverse of sine, if I take the sine of both sides of that equation like we did in the last problem, I end up with that. Are we good with that? Nothing, no fancy tricks there. I just took the sine of both sides. If I want to take the derivative of the first equation, this one up here, I can just take the derivative of this. Since these are equivalent statements, I'll get the same answer. Yes? So do the easy part. What's the derivative of x? 1. Good. What's a derivative of sine of y? Good. Very nice. Cosine of y, y prime, because it's implicitly differentiated. I think my clicking is out of order here. There we go. That's what, I don't know why that triangle's there, but that one, I was going to save that for later, but here it is. So here's my angle y. My setup here is taking x, so it's just like we did in the previous problem. X is the opposite side, y is the x is the hypotenuse, 1 is the, let me try that again. X is the opposite side, 1 is the hypotenuse, sorry. That makes the third side 1 minus x squared. So implicitly differentiate both sides. I get cosine of y, y prime, or dy dx. It doesn't matter. It's the same thing. Move the y to the other side. I get that. Which would be nice to stop there, but I don't want a y in the formula. So then I put in what the cosine of y is equal to, and that comes from the triangle. Cosine is adjacent over hypotenuse. So this becomes that. And that's where that formula came from. If you look on that previous slide, or look in your notes for the derivative of the inverse sine of u, it's that. The only difference is, since I'm doing a u, you got to include a u prime there, the chain rule. I would not expect you to be able to regurgitate this process. However, like I said earlier, I do think it's important that you see where these come from. If you want to find the why the formula for the derivative of the arc cotangent is what it is, you would go through the same process here. Okay, write it as the cotangent of x is equal to, or inverse cotangent would be equal to, of x would be equal to y, switch it around, take the derivative, all kinds of fun stuff ensues. Okay. But yeah.
Can you explain how you set up the triangle?
I know that there is some angle that when I do the sine of it, I will get x.
So did you?
And x is the same thing as x over 1. Sine is opposite over hypotenuse. So here's my angle y. Opposite is x, hypotenuse is y. Pythagorean theorem to find that guy.
How do you want to do it based on that and not the cosine?
Because I need this before I do the cosine. The cosine comes about when I take the derivative. So the triangle is based on the original function, not the derivative. Okie doke. This is fun, right?
Yeah.
Yeah. Well, the good news is we're done. Except for one simple thing. When I talked about taking the inverse, and when I just derived that inverse sine of x, that's based on x, and like I said, what happens if it's u? So I'm just going to go through a couple quick examples. It becomes ridiculously easy if you can recognize what u is. So in this first problem, u is 2x. So just make sure that you ask yourself what's u before you start plugging into the formula, because you're also going to need to find u prime in each one of those formulas. Okay, and then clean things up. Notice that this is the quantity u squared, not, so that's 2x quantity squared, not 2x squared. So the 2 has to be squared also. John.
So on a quiz or test, if we just were asked to find the derivative of arc sine of 2x, we could just
Plug and chug into the formula. I'm not going to expect you to derive it. Okay. A couple more examples, just go through these quickly. C gets a little nasty because of the just the nature of the function in there, and that can clean up a little bit. And then, of course, we don't want to throw an e in there. So applying the secant formula there, then those e to the 2x's would cancel, and we get that as a final answer. Notice e to the 2x raised to the second power, you multiply the powers there. Awesome. There are 24 of them. Woohoo! All of these 24 things are all variations of derivatives that we've done already. Some of them should be burned into your brain by now. For instance, number 5. Okay. Derivative of a constant is 0. Number 6. What's the other name for number 6? Power rule. How about number 2? Anything fancy going on there? No, it's what we use to take the derivative of x squared plus 3x minus 2. Take the derivative of each individual part. How about number 4? Quotient rule. Number 7. Ridiculous. You should know that one. Don't write that one down. 8, 9, 10, 11, and 12 are all the new stuff we've just done in chapter 5. Derivatives of exponentials and derivatives of logs. The first 7 is stuff we've been doing since September. I don't know if you saw it when I flipped before, but 13 through 24, all the trig stuff. 19 through 24 are all the ones we just did today. 13 through 18, some of those we've been doing for quite a while, some of them are fairly new. We have no more derivative rules. Everything from this point on is just applying this to different scenarios. We'll be doing more word problems, we do some volume and area stuff. Volumes are really cool, that's chapter 7. But we're done with the derivative stuff. After 5.7, which is integrals, we'll have another chart just like this that'll summarize all the integral properties we've had all year long. No new integrals from that point on, just applications. Okay. This, by the way, in case you didn't see, is in page 3, on page 378. Don't write down formulas that don't make any sense to you. For instance, if you have no idea what number 3 is telling you, then don't write it down. What is number 3, by the way? Product rule. By now you should know the product rule. If you need a refresher, write it in a form that makes sense to you. If this makes sense to you, great, write it down. If it doesn't, then write down whatever you have in your notes that has made sense to you from September. Don't write number 5 down. You should know by now that the derivative of 2 is 0. Right. 8, we didn't do a lot of work with, but it is there if you want to take the derivative of some absolute value. Okay, we good?